So I want to talk about some joint work with students of mine here at Penn. And maybe to start off, I sort of want to note to what everyone knows, which is that at this point in 2024, machine learning is getting really good. We're getting really good at predicting all sorts of things, the completion of text prompts, important things like whether or not to apply the brakes. But of course, even in applications of machine learning in which we are pretty good at predicting things, prediction technology is necessarily far from perfect. And since perfection is unachievable, especially in high-stakes decision-making settings, there have been lots of calls for machine learning to be trustworthy. Right? This is at the very least a fundraising keyword. Trustworthy machine learning. And so the question I want to interrogate in this talk is, what should that mean? What should trustworthy machine learning mean? In particular, what are the semantics of the promise that we are being asked to trust? And what I want to propose as a potential promise in this talk is that a downstream decision maker acting as if the predictions are correct should be a good idea. And we'll sort of think about in this talk how we can make this notion of a good idea precise. But maybe just to hold something in your head, the way I propose to evaluate the trustworthiness of a machine learning algorithm here is through the lens of a downstream decision maker and what their incentives are to act as if the predictions are correct. And of course, this will mean different things depending on what the downstream decision maker wants to do, what kind of scenario they're acting in. We'll set up a utility theoretic framework, and we'll see how to use this perspective also as an algorithm design paradigm to design algorithms that have various kinds of downstream guarantees. And I want to say right off the bat that sort of the proposal will be based on sort of a rich literature on the foundations of probability that is sort of distributed across statistics and economics and a recent computer science literature studying ideas surrounding this idea of calibration, which we'll talk about in a moment. Okay, so prediction for decision making. We'll start very high level and we'll try to get more precise as we go. But I want you to think about the following kind of pipeline where we've got data. Data is used to inform predictions that we make with some kind of machine learning prediction technology. And sort of a standard way to evaluate a machine learning algorithm would sort of draw the box here and evaluate something like the squared error or some other loss of the predictions. But I want to add a third box, which is that these predictions will be consumed by one or more downstream decision makers, and we will ultimately evaluate the quality of our predictions through the decisions they induce. Okay, so what is a downstream decision maker? A downstream decision maker is defined by a few things. So first of all, they've got some action space. These are the things they can do. These are the downstream decisions they might make. They've got a state space. Think of this as represented by d-dimensional vectors, but ultimately this is sort of the decision-relevant state for the decision maker. They would know the utility they would get for each of their actions if only they knew what the state was. Okay, and this is the thing we are going to be trying to predict. And finally, they've got a utility function that takes as input one of their own actions, takes as input the state, and outputs a number. It specifies sort of how happy they are with the action given the state. And crucially, but although we'll argue in a moment that this isn't too restrictive, I'm going to assume that this utility function is linear in the state. Okay, so it can have an arbitrary dependence on the action. The utilities of different actions can be arbitrarily different, but fixing an action, I'm going to assume that the utility function is linear in this d-dimensional state vector. Okay. And so what are examples of sort of settings where the decision maker has a utility function that is linear in the state vector? Well, one very general setting is one in which the true realized state is going to be one of d finite possible realizations. Maybe think of this as like a weather outcome. And the utility function of the agent is entirely arbitrary. It's a function of one of the d deterministically realized realized states together with the action. But the object that we are predicting is a probability distribution over these actions. Or, sorry, a probability distribution over the states. Okay, so the utility function in terms of the sort of realized discrete states can be entirely arbitrary, but the decision maker is risk neutral in that given a probability distribution over states, they evaluate their utility and expectation over those states. A utility function like this will be linear simply because of linearity of expectation. So for example, the states we are predicting, the d-dimensional vectors, can be probability distributions over the discrete outcome, the probability of rain or snow or sun. The actions might be, deciding what kind of, equipment to pack with you to New Haven. And you could have some utility function defined arbitrarily in terms of these discrete outcomes when what you care about is your expected utility. This satisfies the linearity assumption. But this isn't the only kind of example that satisfies this linearity assumption. Here's another example. So suppose I were driving to New Haven. So this is Google Maps up here. But it's not showing, I didn't bring it up to show the current traffic conditions. This was predicting what the traffic would be like, which, at a time that was, at the time, next Monday. Okay, so this is a prediction of future traffic conditions. Perhaps, we can think about the vector, the sort of payoff relevant vector that is being predicted here as the set of all possible road congestions, sort of a vector of length equal to the number of roads in this network. The actions that I might have available to me are the set of all home to work routes, or the set of all routes from my home to Yale. And the utility function, if I choose a path in this network and the state is realized as some vector of congestions, is just the negative sum of the congestions on the roads along the route. Okay, so this is another example of a kind of utility function that is linear in the state. So that's not to say that this assumption is without loss of generality. The assumption is very important, but it's not hard to come by utility functions that are linear in the state, if only because expectations are linear. Okay. So I told you what a decision maker is. Let me tell you now about the sort of learning setting I want to think about, which is the sequential prediction setting. So what we have is a context space X. These are the features relevant to the prediction task. So this might be, like the day. Is it a weekend? It might be it might be sort of barometric readings if I'm predicting weather. This could be anything. It's information the learner knows before they need to make their prediction. We've got our prediction or outcome space. This is the same as the state space that the downstream decision maker ultimately cares about. This is some subset of d-dimensional real valued vectors, and I'm going to assume now that it's convex. So for example, if I'm predicting the probability of a discrete state, this would be the probability simplex, that's convex. If I'm predicting road congestions, this might be the set of legal flows or something, that's convex. And then in rounds, okay, and there's going to be a time component here. In a series of rounds, what happens is that the learner observes some context, the features that are relevant to the prediction task. Then they produce a prediction. The learner produces a vector valued prediction. It's a prediction for what the state is going to be. And then the learner observes what the true state is. Okay, and we'll talk about what the learner's goals might be, but this is sort of the environment in which the learner is operating. They see features, They predict a vector valued state, and only then do they see what the true vector valued state was at that round. And we're not going to assume any kind of nice distributional process through which the outcomes are generated. The outcomes could be generated sort of in an arbitrary adversarial way. And the reason for that is because if we can get positive results in this setting, then we don't have to worry about our assumptions about the environment failing to hold because we haven't made any. Okay. And so let's think about prediction for decision making. So we've got this agent, one or more agents, and they've got this utility function. They've got this action space. If they knew what the realized state was going to be before they had to take their action, then it would be very easy for them to decide what action to take. They would just best respond. They would choose the action that maximizes their utility given the state, right? So if they could look out the window and they knew it was raining already, they would just take an umbrella with them. The difficulty is, in this scenario, they have to act before the state is known. Okay, so they have to decide, are they going to pack an umbrella with them to New Haven? They don't know whether it's going to rain, on Monday, say. And so the question that I want to ask, and then this is, getting a little bit closer to specifying what I'm going to want to mean by, is the prediction trustworthy, although still a bit informally, is suppose, of course, the agent doesn't know what the realized state is going to be. They can't see the future, but we've given them a prediction for what this realized state is going to be. I want to ask, is it a good idea to trust the prediction insofar that they will act as if the prediction was correct? Right? Is it a good idea for them to play their best response to the prediction as opposed to doing something else? Okay, this is, again, we still need to formalize this a bit more, but this is sort of the question that I want to attach to, is this prediction trustworthy? Okay. And so let me remind you what calibration is in case you've forgotten or, maybe it's been a while. So calibration is sort of a very simple sanity check condition on predictions. You've probably, if you've seen it before, you've probably seen it in the context of a one-dimensional binary prediction. So things like prediction for whether it's going to rain or not. Okay, so when you see it in that context, it's usually defined as follows. A weather forecaster is calibrated if on all of the days for which they predict a 20% chance of rain, it actually does rain 20% of the time. And on all of the days for which they predict a 30% chance of rain, it actually does rain 30% of the time. Okay? That's calibration for sort of a one-dimensional binary outcome. But another way to sort of express that condition that generalizes to d dimensions is to say, look, if I've got some joint distribution over predictions s hat and realizations s, what I want is that the expectation of s conditioned on the realization of the prediction s hat should be equal to s hat. Okay, for all predictions s hat. This just means that the predictions themselves should be unbiased. They should have no statistical bias, conditional on the predictions. Okay, so it's a sanity check for forecasts that sort of predictions should be self-consistent. If a weather forecaster really knew the probability of rain, when they said there was a 20% chance of rain, what that meant was that the rain outcome would be realized by a Bernoulli random variable with mean 0.2. Then their predictions would be calibrated at appropriate rates. Of course, it's possible to be calibrated without being correct, right? So calibration is a weaker condition than correctness, but unlike correctness, calibration has the merit that it is audible. It is not possible to sort of determine whether predictions are correct. In fact, like, you can sort of read up in the philosophy of science on the reference class problem if you want to think about people sort of, or if you want to read about people wondering at length whether individual probabilities, like the probability of rain, are even coherent. But calibration is a purely statistical quantity. You can check it and you can enforce it. And calibration instills trusts in predictions in the following sense. This theorem is so simple, I'm gonna like prove it to you on the next slide. And basically it just comes from understanding the definition of calibration. If I've got a forecasts that are calibrated, then for any downstream agent, no matter what their utility function is, so long as it is linear in the state, following the best response action, that is, choosing the policy mapping predictions to actions that simply treats predictions as if they were correct and best responds to them, uniformly dominates any other prediction to action policy, in the sense that if I look at the agent's expected utility of following the policy of trusting the predictions and best responding to them, that expected utility is higher than it would be had they followed any other policy mapping predictions to actions. Okay, so like in a slogan, if the predictions are calibrated, one implication is that a downstream agent can't do better than to trust the predictions. And I think that even though this is very, very simple, it's worth understanding, because I think this is one of the primary reasons to like calibration as a condition. It's not for its own sake that things should that statistical predictions should pass sanity checks. It's because calibration has this very strong decision theoretic property. Okay, so this is like an exercise in understanding the definition. So let's just go through the proof. So suppose F star is the best response policy. F star just takes as input a prediction and maps that to the action that best responds to the state that we predicted. We want to understand what is our expected utility for playing the best response policy in response to these predictions that are being made. Okay. So there's a joint distribution over states and predictions, S and S hat. We can just break that down into a nested expectation. First, we take the expectation over the predictions S hat, and then on the inside, we take the expectation over the true realizations S, conditional on the prediction S hat. Now remember, the one thing we've assumed here is that the utility function is linear, which means that we can bring this expectation inside of the utility function. Okay. Now, what does calibration tell us? Well, calibration tells us that the predictions are unbiased, conditional on themselves. And so the expectation of the state, S, given that we've predicted S hat, is just S hat. And now at this point, we're looking at the utility that we would get for playing some action if the true state was S hat. And so at this point, it's a really good idea to play the action that best responds to S hat. Definitionally, that is the utility maximizing action if the state were S hat. And so the utility here is higher than the utility of any other action. In particular, it's higher than the utility of the action that would have been suggested by any other policy mapping states to actions. Okay, that's the key inequality. The other inequalities we can sort of just repeat in the backwards direction to get back that, again, the left-hand side, the expected utility of best responding to the forecasts is only higher than the expected utility of playing any other policy mapping forecasts to actions. Okay, so very simple, but maybe worth understanding. Right, so this is something that holds simultaneously for every single downstream agent, no matter what their utility function is, so long as their utility function is linear in the state. Right, it's sort of an incentive compatibility kind of constraint. It says that acting straightforwardly, trusting the predictions and best responding to them dominates any other policy mapping predictions to actions. Okay. So calibration is great. Maybe we can end the talk here. Let's just check a couple of things. So there's good news and, as you might expect, bad news about calibration. Okay, so the good news, we've talked about it. Calibrated predictions mean what they say And in particular, they have this nice decision theoretic property that trusting them and acting accordingly is better than any other strategy that maps predictions to actions. And even better news, since the seminal work of Foster and Vora, we have known that it is possible to produce calibrated predictions even in online adversarial environments, even in strategic environments where the state isn't following any nice process, but might be controlled even by an adversary. Okay, so like, it's not that the good news about calibration is of the form, if pigs can fly, dogs can dance. Like, it is actually constructively possible to make predictions even in adversarial environments that are calibrated. So that's great. However, there's some bad news, and the bad news is basically that calibration scales very badly with the dimension of the prediction space. So traditionally, when people talk about calibration, they're talking about predicting states that are sort of one-dimensional and binary valued. Is it going to rain tomorrow or not? And in that setting, you can really run these calibration algorithms. But remember, like, what calibration is asking for, it's asking for unbiasedness of the predictions, conditioned on every value of the predictions themselves. And like, if you think about how many predictions there are, if we're predicting in a d-dimensional space, even if we discretize, there are going to be sort of exponentially many distinct predictions in the dimension, which is maybe giving you like a hint as to what the difficulty is going to be. And in particular, like, if we look at for the best known algorithms, both the computational and statistical complexity of maintaining calibrated forecasts against an adversary, they both scale very badly with D. So the computational complexity of calibration in adversarial settings grows exponentially with D. And the rate, we're never going to get perfectly calibrated forecasts. The rate at which we know how to get calibrated forecasts also is really bad in the dimension, right? So if we're just predicting probability of rain, we can sort of get calibration error, that grows only like t to the 2/3, but the rate gets exponentially worse with the dimension. So calibration is sort of a non-starter if we're in a setting, as we oftentimes are, where the dimension of the payoff relevant state is more than one, right? Like, think about this kind of routing example. The dimension is the set of all traffic congestion vectors, which has D equal to the number of roads in like the road network in the United States. So this is a problem. And so what I want to think about is whether there might be something short of calibration that doesn't have all of the guarantees of calibration, but maybe has enough of them for particular use cases and is more computationally tractable. Okay, so in particular, like, just to put a goal in your mind here, calibration has the nice property that it offers these sort of decision theoretic guarantees simultaneously to all downstream decision makers. But it might not be that we're interested in all downstream decision makers. We might have some inkling about what decision makers in our context care about. And maybe we can sort of try to sort of target our predictions more specifically at some subset of the decision makers, give up on guarantees for all of them, but in return get something that is sort of computationally and statistically tractable. Okay. So here's an intermediate goal. I want to talk about making predictions that are statistically unbiased, conditional on some collection of events. Okay, so what's an event? An event basically is some arbitrary function of the things that I know at the time that I am making my prediction. So it can depend on any context that is available. It can depend on my prediction itself. It could depend on history. And it's a binary function. It says, okay, given what I know, given what I predicted, is the event active today or not? Okay, it selects a subsequence of the rounds as a function of the context and the prediction. And a sub-goal that, like, we're going to hope is useful is that maybe what I want to do, given a collection of events, is maybe what I want to do is I want to make predictions that are statistically unbiased or have low statistical bias, conditional on each of these events. By which I mean, if I sum up over all of the rounds at which I make predictions, and I use one of these event functions to sub-select out the set of rounds for which the event is active, and I look at the difference between my prediction in those rounds and the outcome in those rounds, I want that difference to be 0 or close to it. I want the average of my predictions to equal the average of the outcomes, not just overall, but simultaneously on the subsequences defined by each of these events. Okay? And if you look at this, calibration is the special case in which the events happen to just select out the rounds for which I make each of the particular predictions I could make. The difficulty is there's exponentially many such events in d dimensions because there's exponentially many predictions I could make. Okay, so calibration is useful but hard to obtain. So 2 questions I want to ask are, look, like maybe calibration is hard to obtain, not because there are exponentially many predictions that I can make, not because sort of my action space as the learner is exponentially large, but because I'm insisting that those predictions be unbiased, subject to only or subject to a huge number of events, subject to exponentially many events. And so maybe if I ask for something weaker, if I ask for still d-dimensional predictions that are unbiased now, subject to maybe only a polynomial number of events, maybe I can make these kinds of predictions efficiently, and hopefully, if I select the events appropriately, the predictions that are no longer fully calibrated but unbiased, merely subject to this, now artisanally chosen but modestly sized collection of events, maybe those are going to be useful for something. So that's what I want to do in the next 10 minutes. Okay, so like, what are the events we might focus on? Suppose we have not every possible downstream decision maker, but suppose we've got like k downstream decision makers in mind. Okay, so the decision makers have one of these k utility functions, u1 through uk. Okay. I claim calibration was sort of a little bit overkill to sort of convince them to best respond to our predictions. Well, how come? Like, let's consider a single decision maker in a toy setting where Alice, say, we're predicting the probability of rain, and Alice is just deciding whether she's going to bring an umbrella or not. And suppose her utility function is really simple. She gets utility 1 for sort of choosing the action that matches our prediction, and 0 otherwise. And so her best response function is going to decide to bring the umbrella if the probability of rain is greater than 50%, and otherwise she won't. Okay. Now, if I ask that my predictions are calibrated, like calibration in a sense is really sort of wringing its hands about the difference between a 98% chance of rain and a 97% chance of rain and a 96% chance of rain, because the predictions need to be unbiased, conditional on the predictions themselves, no matter what those predictions are. But of course, the distinction between a 98% chance of rain and a 97% chance of rain doesn't really matter for Alice's decision-making problem. She's just sort of thresholding at 50%. Okay? So these are the events I want to focus on. For each of the downstream decision makers, for each utility function u, and for each action they can take, I want to look at how that agent's best response function partitions the state space. In particular, like for each action A, I'm going to define an event equal to the set of predictions that causes the agent to best respond with this particular action A. So for Alice, as we described her, there's only 2 events. There's the event that we predict greater than a 50% chance of rain, and there's the event that we predict less than a 50% chance of rain. And more generally, for any agent, this sort of partitions the state space into a number of events equal to the number of actions they have. Okay, crucially independently of the dimension of the prediction space. And so, these events are disjoint for a single agent. For multiple agents, the events are not disjoint, but that's okay. We haven't asked anywhere that our events be disjoint. And the thing that I want to propose might be a good idea to do, this is related also to something called decision calibration, is to produce a sequence of forecasts such that the forecasts are unbiased, not just overall, but are unbiased conditionally on each of these best response events. Okay, so I want the forecasts to average out to the outcomes, not just overall, but also conditionally on inducing each of our downstream decision makers to play each of their possible actions. Okay, so it's kind of like calibration, except like the number of events here scales only with the number of downstream decision makers we care about cross the cardinality of their action space. It does not depend on the dimension. The calibration conditions are of cardinality that scale exponentially with the dimension, and that's sort of the thing we're going to gain here in terms of efficiency. Okay, so here's one simple fact. If I've got an agent who's got some utility function U, and we are making predictions that are unbiased, subject to the best response correspondent of that agent, and our agent decides to trust our forecasts and act accordingly, just best respond to our forecasts, then they will have no swap regret, which means that they are guaranteed that no matter what the sequence of outcomes is, the utility they get from trusting our predictions and best responding is only higher than the utility they would have gotten had they counterfactually sort of applied any policy remapping the actions they took to other actions and played that instead. Okay, and this is true not just for like one agent, but simultaneously for every agent we targeted that is ingesting our decisions. Okay, so we might be able to do this for polynomially many downstream agents. For example, every agent, well, yeah, we'll get to an example in a moment. And in fact, like this dependence on the number of agents here turns out to be artificial. So at this EC conference, there's a paper you'll be able to see presented by my student Myra that shows how to make predictions that induce no swap regret for all downstream agents using similar techniques. We can do other things as well. So, this idea of conditioning on the action induced by the downstream decision maker, this idea works pretty well if the downstream decision maker only has a modest number of actions, only has polynomially many actions. But remember, like, our whole premise here was sort of getting away, like the reason we were worried about calibration was it requires conditioning on exponentially in D many actions, exponentially in D many events. And so switching to conditioning on the action of the decision maker would not help us if we were in a setting in which the downstream decision maker also had exponentially in D many actions. We'd have to do something else. So let's think about a scenario where that might be the case, and maybe think about here this problem I mentioned at the beginning of a downstream decision maker who chooses a route in a D-dimensional network to drive along. Okay, the dimension here is D, but the number of routes in a graph that has D edges can be exponential in D. So more generally, in an online combinatorial optimization problem, we've got some set of D base actions, for example, the roads in the network, and our decision makers have feasible sets of actions which are subsets of the power set of these base actions. They can choose subsets of the actions. For example, they might have as their action set all of the paths in the network going between S and T. Okay, and so in an online combinatorial optimization problem, however, the utility for each agent will decompose linearly across the base actions, across the edges. So the state encodes some gain along each of the edges. And the utility that an agent gets for playing some action is just the sum over all of the base actions contained in the compound action they played of the gain that they get for that base action. Okay, so it's a setting with a lot of actions. There's up to 2 to the D actions, but there's this sort of D-dimensional linear structure. And what we might want in a setting like this is, let me generalize swap regret a bit and call it conditional regret. Okay, so given a collection of events, let's say that an agent has alpha regret conditional on those events if simultaneously for each of those events, when we look at the utility that they got on the subsequence of rounds for which that event was active, that was at least the best utility they could have gotten for the best fixed action on that subsequence. Okay, and we want the, if you've thought about regular regret before, it asks for a condition like this marginally over the whole subsequence. But here we're asking for it simultaneously on many different subsequences defined by these events. The best fixed action might be different on each of these subsequences. Okay, swap regret is just a special case where the subsequences are defined by the indicator functions that I play at each of the actions. Okay, so we don't want to condition on the event that the downstream agent played a particular action anymore, because there's like 2 to the d conditioning events if we do that. But we want to instead take advantage of the fact that the downstream decision maker's utility function has this linear structure. And essentially what we want to condition on now is just the event that our prediction induces the downstream decision maker to play some compound action that that sort of includes within it each one of the base actions. Okay, so the event that our prediction induces the downstream decision maker to play a route that includes, Walnut Street. Okay. Details aside, like what you can get by walking down this path is that you can make predictions that are simultaneously useful for many downstream decision makers. For example, maybe every downstream decision maker in the routing game defined by every ST pair in the graph, such that if they trust the predictions and act accordingly, best respond to them, they will have no regret to the best route in hindsight, not just overall, but simultaneously on whatever polynomial number of conditioning events you decided to think about. So they are playing the best, they're doing as well as the best route in hindsight on rainy days, on Mondays, on national holidays, on days when the best route involves I-76, on days when the best route takes surface roads after a Phillies game, anything at all that you can define as a function of context, history, and your own prediction. There are more applications, but I'm running low on time, so let me skip those. I'll just mention them briefly at the end. Let me just sort of state for you like what we can actually do. Okay, so all of this was about useful things you could do if only you could make predictions that were unbiased, subject to polynomially many events in high dimensional settings. Okay, well, it turns out you can. There's a online prediction algorithm that makes these d-dimensional forecasts in an adversarial setting that has sort of worst case bias with respect to any collection of conditioning events that scales only with the square root of the log of the number of conditioning events. So you can have a lot of conditioning events, and with square root of t, these are sort of like statistically optimal bounds. And the algorithm is efficient whenever the dimension is polynomial and the number of conditioning events is polynomial. So the per round running time of the algorithm depends polynomially on the dimension and the cardinality of the number of conditioning events. So if we asked for full calibration, this would again run an exponential time because there are exponentially in D many conditioning events. But in the sort of examples we've seen, it is sufficient to take a small number of conditioning events, in which case this is efficient. And I don't have time to talk about what the algorithm looks like, but if you're into equilibrium computation, you might enjoy it. It's sort of solving a zero-sum game at every round, but you have to be a little bit careful because it's a big game, because the prediction space is exponential in D, but it's got enough structure so that there are efficient solutions for it. Okay. So in my last minute before questions, let's say, just to summarize, calibration is great. Right, it has this strong semantics for trustworthiness, which are that trusting the predictions and acting accordingly is guaranteed to be the optimal policy, mapping predictions to actions. But it's really hard to get fully calibrated forecasts in high dimensional settings. What we can do is make predictions that are unbiased, subject to any polynomial number of events. And by picking those events carefully, we can get strong downstream guarantees. So we get new algorithms for forecasting to give any polynomial number of downstream decision makers no swap regret. We've got this extension that'll appear in a couple days in this conference that Myra will present that actually lets you make forecasts that get at the optimal rate no swap regret for all downstream decision makers. We can get these new efficient conditional regret guarantees in combinatorial optimization problems. There are a bunch of applications just to sort of uncertainty quantification that I didn't have time to tell you about. And you can also, places where calibration is useful but cumbersome because of the sort of high dimensional dependence, you can often swap out these more refined kind of guarantees and get efficient mechanisms. So Natalie and Han will present a paper in which we get new results for principal agent problems. And I think that this is sort of a useful way of thinking about algorithm design and predictions generally, and so I suspect there will be more applications. Just one final thing, just because of the topic of this workshop. Here, we talked about statistical bias, which was about means. But it's also possible to have similar results for other distributional properties like quantiles and mean variance pairs and value at risk, conditional value at risk pairs. And if this sounds familiar to you, maybe from the property elicitation literature, it should. It turns out that you can characterize exactly which are the distributional properties that you can calibrate to, and it is exactly those distributional properties that are elicitable in the sense of property elicitation. Okay, thank you very much. Sorry I wasn't there in person. And if there's time, I'd be happy to take a couple questions. If anyone's still there.
Do I use the microphone or what?
Yes.
Thank you, Aaron. Fantastic, really interesting talk. So for instance, if we are thinking like, stock market forecasts, okay? So if someone is forecasting excess returns, does it mean like, that we should not trust that, because immediately if investors, trust that, forecast, everyone would use that and that opportunity is vanished.
Good. So I think what you're getting at is, well, okay, there's two things. So first, the fact that the best policy mapping predictions to actions is to trust the forecasts and best respond. That does not mean that trusting the forecasts and best responding will lead to an outcome that is sort of good for you in some objective sense. Because if the forecast could still be uninformative, it just means that any policy map, if the forecasts are uninformative, any policy mapping forecasts to actions will lead to poor outcomes, including the best response one. So maybe that's like the first thing to understand. You're also getting at sort of a scenario where the state that I am predicting will be a function of the predictions that I make, because the different decision makers will best respond. Our results still go through in that setting. You need to re-randomize for each agent, but like what you'll get basically is convergence to correlated equilibria, which means that, again, as a function of the forecasts, you won't be able to improve on best responding to the forecasts, but that doesn't mean that you will do well in some objective sense. It might be that, yeah, if you don't have any signal that other people do, there's no function of the forecasts that does well in an objective sense. I don't know if that answered the question.